Okay, these are some more problems from section 9.4, and we're just trying to check the convergence or the divergence of the series and use the test that or state the test that we used. And a lot of these times, like I said, you'll use the ratio test 95% of the time. So let's give it a shot. So number 41, we'll try the ratio test. And remember, we're going to look for the limit of a sub n plus 1 over a sub n, and that limit will equal L if that's less than 1. It converges if it's greater than 1, it diverges, and if it's equal to 1, we've got to try something else. So we'll give this a go here. So this would be 3n plus 1 over n plus 1 to the third, 2 to the n plus 1, and then we'll multiply by the reciprocal of that, which would be n cubed 2 to the n over 3 to the n. Then we can break this up as 3 times 3 to the n, all right, over, 3 times 3 to the n, and this is going to be n plus 1 cubed and 2 to the n, times this same thing. And then we can cancel the 2 to the n's and the 3 to the n, so we've got 2 over 3, and then we've got n cubed over 2 times n plus 1 cubed. So we can take out the 3 halves, we can bring that out in front of the limit, constant multiplier type rule. And then I'd have n cubed on the top, and I just multiply this out. You didn't really have to, but I could multiply it out just using one of our special product rules. And we get n cubed, 3n squared, 3n plus 1. That's kind of using the Pascal's triangle. And you can see that the highest degree term, if you look at it's a rational expression, so the limit as n approaches infinity is just going to be the ratio of the coefficients of the highest degree terms. That's going to be 1. So it's going to be 3 halves times 1, which is 3 halves, which is greater than 1. Therefore, the series converges. L is greater than 1. Implies the series converges. That's L. Okay? Now, we don't have to use we don't have to worry about absolute values because these are all positive terms. Okay? Let's take a look at 42. 42, n, natural log of n over 2 to the n. Again, these are positive terms. Okay, natural log is going to be positive for n greater than 1. Okay, so we use the ratio test again. So we'll add 1, n plus 1, natural log of n plus 1 over 2 to the n plus 1. And these are kind of small, so you can always zoom in if you have to, I think, and pause it if you want to check these things out. And this is going to be, and then times this reciprocal to the n times natural log of n. And what did I do here? Okay, I just broke up the 2 to the n and 2, so I could cancel out this 2 to the n's, get that kind of out of the way. So I have 1 half, and then I've got all these things going on with the n plus 1 over n, and then the natural log of n plus 1 over the natural log of n, 1 half. And this is the limit. So what I did was I brought the 1 half out using the constant rule, and then I remember the limit of a product is the product of the limits, so I broke this up into two different limits. And there's lots of ways to do this. You can do this the intuitive way. You can just substitute infinity in, but we can also use L'Hopital's rule, so that might be a little nicer with a logarithm one. Because if I substitute in, I get infinity plus 1 over infinity, which is infinity. And here the natural log of infinity plus 1, that's going to be infinity because that goes up and up and up. Well, gradually like that, pardon me. The natural log of n is also going to infinity as n goes to infinity, so that's infinity over infinity, so I can apply L'Hopital's rule. So I've got 1 half. If I take the derivative of the top, I get 1. Derivative of the bottom, I get 1. So 1 over 1, which is just 1. And if I take the derivative of the natural log of n plus 1, I get 1 over n plus 1. And if I take the natural log of the derivative of the natural log of n, I get 1 over n. I can invert and multiply, so that'll give me n over n plus 1, which pretty much looks like this. I also have an infinity over infinity again, so I can use L'Hopital's rule again. Now this limit here was just 1, so that's kind of absorbed in the 1 half. If I take the derivative of this, I get 1 over 1 again, so I get 1 half times 1. The limit of this is just 1, which is 1 half. 1 half is less than 1, so that 1 half is the L, so L is less than 1 implies the series converges. All right, and then number 43. Like I said, I hope you can see this. Maybe I can zoom in just a little bit here. So, oops, that's a little too much. A little less, okay. All right, so this is 43. It's kind of tight at the end, so I'll try to talk through it anyway. Okay, so again, we're going to use the ratio test. These are all positive terms, n factorial over 2 plus 1 factorial, we use some of our little factorial tricks. And we take the limit as n approaches infinity of n plus 1 to the factorial over 2n plus 1 factorial. Remember, every time you see an n, you got to put n plus 1. And the times the reciprocal, this 2n plus 1 over n factorial. And this is n factorial. Now we can rewrite this 2n plus 1 as, that's 2n plus 2 plus 1 is 2n plus 3 factorial. Now what I can do in order to get that to kind of work with this is I can write 2n plus 3 factorial is the same thing as 2n plus 3, well, times 2n plus 2 times 2n plus 1 factorial, because that's going to go all the way down. I probably could have put these terms on the other side. But either way, you can write this as 2n plus 3, and then 2n plus, we subtract 1, then times 2n plus 2 times 2n plus 1, etc., and that's because of the 2n factorial. All right? So I should have written it this way first, okay? I don't know why I chose to do it like that. And then I have the n factorial here on the top. Well, this is the same thing as n plus 1 times n factorial. So I have n plus 1, n factorial, n minus 1, etc. goes on. So this is n plus 1 times n factorial. And now I can cancel out the factorials because those are a little bit awkward to work with. And now I have n plus 1 all over, okay? And these 2n plus 1's factorials are canceled. So over 2n plus 2 times 2n plus 3. So that's what was left. Okay? Now I think this is it. If I factored out a 2 here, this is the same thing as 2 times n plus 1. Let me write it down here. 2 times n plus 1. So those n plus 1s are canceled, so I end up with 1 over 2 times 2n plus 3. All right? Well, if I take the limit as n approaches infinity, I've got 1 over something very, very, very large, so that's going to equal 0. Since 0 is less than 1, it converges. L is less than 1, it converges. Okay? So I hope you get how we rewrite this 2n plus 3 factorial as 2n plus 3 times 2n plus 2 times 2n plus 1. It would keep going down there, but now we can just rewrite this as a factorial. And the same thing as n plus 1 factorial would be n plus 1 times n minus 1, etc., which is the n factorial part. Okay, I hope those help.